Assessing the performance of subgrade and unbounded pavement materials and their effect on pavement distress of Alaba-Sodo Exisiting Road, Ethiopia. Abstract. Since material properties play a significant role to determine the performance of pavement layers. In Ethiopia, nowadays, pavement distress is the main problem of roads affecting its intended purposes. This research study is undertaken at Alaba-Sodo Road, which is located in SNNPRS, is one of the roads affected by distresses. The main objective of this study is to assess the performance of subgrade and unbound pavement materials and their effect on pavement distress through condition survey and laboratory tests. Among the total sample units of 199 along the selected road sections, 71 sample units were selected by using systematic random sampling technique. For those selected sample units, PCI values were determined in order to know the stations for sample collection for laboratory tests. Based on the PCI values, 8 sample locations were identified. Out of these, 6 locations were selected from severely distressed and 2 locations were selected from good sections. From 8 identified sample locations, 3 samples were taken from each layers of subgrade, subbase, and base course. Therefore, total of 24 material samples were taken for the laboratory tests. The major tests such as Cbr Test, Compaction Test, Atterberg limit test, Sieve Analysis were conducted for the above-mentioned 3 layers, and ACV, AIV, LAA, and Flakiness Index were conducted only for base course material to check performance of the pavement materials. Out of the surveyed 71 sample units, 1.41% is excellent, 5.63 is very good, 14.08% is good, 23.94% is fair, 28.17% is poor, 21.13% is very poor, and 5.63 is failed. The overall laboratory test result shows that the distresses that are frequently observed on the road surface were significantly influenced by subbase and base course materials. Keywords: performance of subgrade and unbounded materials, OSHTO and ERA standards, geotechnical properties, pavement condition index, pavement distress. 1. Introduction on background. Subgrade and granular material layers must be investigated and constructed properly thoroughly in order to achieve the overall desire of pavement performance. In Ethiopia, nowadays, pavement distress is the main problem of roads affecting its intended purposes. And it is mostly characterized by failure of all kinds, like surface deformation, cracks, disintegration, surface defects, etc. There is no just one reason for each type of failure. Factors affecting the pavement performance are climate, material properties, structure, and traffic load. ERA, Pram, 2013. The research area: Alaba-Sodo Road is the main part of Addis Alaba-Sodo Abamint Road, and which is flexible asphalt paved road. This study only focuses on Alaba-Sodo, 68 km long and one of the reconstructed roads in Ethiopia, which is located in the SNNPRS Ethiopia, and its operation was started in 2010. It is a 2-lane paved 7m wide carriageway with 1.5m gravel shoulders on each side. 2. Statement of the problem. The maintenance of the road to well-accessible asphalt standard is considered to have a crucial role in road performance. But currently the Alaba-Sodo road pavement is prematurely damaged by serious distress with alligators/fatigue cracks, rutting, potholes, block cracking and others cracks and disintegration that can cause traffic hazards, taking long time for travel, affecting economic and industrial growth of nearby zones and cities like Wolata, Kambata, Hadiyah, Shashmin, and Hawassa. The accessibility, users' comfort, and national/social development of the above-mentioned zones and cities and increasing vehicle operating cost are directly and indirectly affected by road distress. Therefore, this research has been done in order to assess the performance of subgrade and unbound pavement material quality and to relate the material quality with the pavement distresses. Because the characteristics of subgrade, subbase, and base course layer material properties have a considerable impact on the performance of the pavement. 3 objectives. 3.1 General objective. The general objective of this research was to assess the performance of subgrade and unbound pavement materials and their effect on pavement distress. 3.2 Specific objectives. To determine the types, severity, and density of the pavement distress based on Pavement Condition Index, PCI. To assess the performance of subgrade and unbound pavement materials by conducting laboratory tests like Atterberg limit, Sieve Analysis, Compaction Test, Cbr, AIV, ACV, LAA, and Flakiness Index. To indicate the effect of performance of subgrade and unbound pavement layers on pavement distress for possible pavement maintenances. 4. Location of the study area. This study is conducted in Alaba-Sodo existing road, which is located in southwestern part of Ethiopia. It connects Addis Ababa, the capital of Ethiopia, with some SNNPRS towns. The distance between Alaba to Sodo is generally 72 km, but the exact study location starts at the Bilate River Bridge, which is 4.5 km away from Alaba town and terminates in Sodo town. Therefore the total length of the route is 68 km. The geographic positions of the total road falls between 7 degrees 18 minutes north latitude to 38 degrees 05 E longitude and 6 degrees 02 N latitude, 37 degrees 33 minutes east longitude. The location map of the study road is shown below. Associated Engineering Consultants, 2006. Figure 1, the Alaba-Sodo road stretch. 5. Research methodology. 5.1 Sample size and sampling technique for PCI. For this research objective, the study road stretch was divided into sections based on preliminary site visit. Each section was divided into sample units. The type and severity of pavement distress was differentiated visually, and then the quantity of the distress was measured. The distress data were used to calculate the PCI for each sample unit. The PCI of the road sections were determined based on the PCI of the inspected sample units within the sections. Therefore, road was sectioned into 5 different sections as shown in Table 1. Among the 5 sections, the 3 sections, Alaba-Adilo, Shonbuj and Bujbadatai, were selected, and the number of these divided sample units as shown in Table 2 with 200 m length according to ASTM D6433 manual. From Table 2, some sections were needed to survey due to problems observed during site visit which stated in remark column. Therefore, the next steps such as the determination of PCI value for each sample unit and average PCI value for each section were continued after determinations of sample units of each section. 5.2 Pavement Condition Survey Procedures. The PCI provides an objective and rational basis for determining maintenance and repair needs and priorities. Continuous monitoring of the PCI is used to establish the rate of pavement deterioration, which permits early identification of major rehabilitation needs. The Pavement Condition Index, PCI, is determined by measuring pavement distress with a numerical indicator based on a scale of 0 to 100. For each distress measured, there are deduct values depending upon the nature of the distress, its severity, and quantity. The deduct values are summed, adjusted to take into account the total number of distresses identified, and then subtracted from 100 to give the PCI index for the pavement, ASTM D6433, 2007. Figure 2, some sample pavement condition surveys on Shonbuj subsection. 5.3 Selection of the sample site and sampling technique for laboratory tests. To assess the performance of pavement layers, of the engineering properties of materials are determined by carrying out different laboratory tests. Samples were collected for laboratory tests as per present pavement condition/pavement condition index, PCI, values. Those locations were selected as severely distressed and non-distressed pavement condition. Hence, it was decided to collect 6 stations from severely distressed section and 2 from good, non-distressed, sections for sampling. 3 samples were taken from Alaba-Adilo section at stations of 1 plus 600-1 plus 800 km, 9 plus 600-9 plus 800 km and 10 plus 200-10 plus 400 km. 2 samples were taken from Shonbuj section at stations of 31 plus 531 plus 700 km and 32 plus 132 plus 300 km and 3 samples were taken from Bujbadatai section at stations of 41 plus 000-41 plus 200 km, 42 plus 800-43 plus 000 km and 43 plus 200-43 plus 400 km and check the effect of pavement layers properties on distresses. Therefore, 18, and 6 samples will be taken from severely distressed sections and non-distressed sections respectively. Generally, 24 soil and aggregate samples were collected from both condition of surface. Hence, laboratory tests conducted were summarized in table below. 6 results and discussions. 6.1 Pavement Condition Survey. The pavement condition survey was made on selected sections by following ASTM D6433 manual methods as discussed in Chapters 3 to establish the stations for taking sample for the laboratory tests. This was done by dividing road pavement into different sections. Each section was divided into different sample units. Pavement condition survey was mainly done in order to differentiate the severely distressed sections and good sections of the road and then to take sample from both sections. Before starting of the detailed pavement evaluation, the entire road length was visually assessed and an attempt was made to identify the current condition of the road and the types of distresses occurred on the road prism. The above Table 6 shows the values of PCI and PCR values that determined from assumed and actual standard deviation of the section Alaba-Sodo and which indicates the pavement needs suitable maintenance works because weighted average PCI value can be rated as poor condition of pavement surface. The above Table 7 shows the values of PCI and PCR values that determined from assumed and actual standard deviation of the section shown below and which indicates the pavement needs suitable maintenance works because weighted average PCI value can be rated as fair condition of pavement surface. The above Table 8 shows the values of PCI and PCR values that determined from assumed and actual standard deviation of the section below and which indicates the pavement needs suitable maintenance works because weighted average PCI value can be rated as poor condition of pavement surface. The above all results and discussion are only about the 3 selected sections out of the total 5 sections of the study. But the remaining 2 sections are almost in the same condition with the surveyed 3 sections. Therefore, this implies that the whole 68 km road rated as poor and fair condition and it needs suitable maintenance works. 6.2 Laboratory test results and discussion. The engineering properties of materials were determined by carrying out different tests such as Atterberg limits, gradation, soil classification, compaction, Cbr, ACV, AIV, LAA, and Flakiness Index tests in the laboratory. 6.2.1 Atterberg limit tests for subgrade, subbase and base course materials. According to ARM Manual, 2013, the subgrade soils with pi values less than 30% and LL60 are suitable subgrade materials. For the seasonally wet tropical climate, all suitable subbase materials shall have a maximum plasticity index of 12 and liquid limit of not exceeding 45, and the base course material, which is the fine fraction of a GB1 material, shall be non-plastic when determined in accordance with OSHTO T90. Therefore, Atterberg test results of all station of the subgrade and subbase materials shows that the materials fulfilled the requirement of the ERA specification. This indicates that the subgrade and subbase materials are in a good performance. This implies that the distress on the surface layer is not because of these 2 materials. Among the total 8 station intervals, only the base course materials of 3 station results fulfilled the minimum requirement of ERA specification. I.e., these test values shows that all station interval materials were fulfilled the minimum requirement of ERA specification except materials at station 1 plus 600-1 plus 800, 9 plus 600-9 plus 800, 27 plus 900-28 plus 100, 41 plus 000-41 plus 247 plus 400-47 plus 600, and which also indicate that the base course materials are not in a good performance. 6.2.2 Sieve Analysis test result for subbase materials. For the entire road stretch, red ash blended with soil is used as a subbase material, and sieve analysis was conducted on this material, and the result shows that the samples which are tested are within minimum and maximum limit of ERA specification. For sample, station 10 plus 200-10 plus 400 was presented in Table 11 and figure below. By similar way, Alaba-Sodo, shown Budge and Budge sections sub-base material revealed that Sieve Analysis represents material remained within ERA specification. Therefore, sub-base material is fair for pavement construction and traffic loading. 6.2.3 Sieve Analysis for base course. For this road section, crushed aggregate has been used as a base course material. All base course materials must have a particle size distribution and particle shape which provide high mechanical stability and should contain sufficient fines, amount of material passing the 0.425 mm sieve, to produce a dense material when compacted. But all stations interval results indicate the materials don't fulfill the minimum requirement of the ERA standard, i.e. the materials are not uniformly graded except the station interval 9+600-9+800, and this implies the base course materials are not in a good gradation or performance. The graph and the table below show the base course sieves analysis according to OSHTO standard for station of 41+000-41+200. Likewise, the gradation results for all remained stations are approximately the same with above station result except at station 9+600-9+800. 6.3 Soil classification for subgrade. In this study the OSHTO soil classification system was used. For this system the sieve sizes of 2 mm, 425 m, and 75 m were used to determine the categories of soil. The table below shows the subgrade soil classification for the station interval 1+600-1+800 according to OSHTO classification system. The above tables all stations of subgrade materials are on group of clayey soils and they were classified by OSHTO, which shows that general rating of a soil fair to poor as a subgrade material. As per Atterberg test, the base course materials satisfied the requirements only at station of 10+200-10+400, 33+600, 33+800 and 32+100, 32+300, but at remaining stations it does not, which have some plastic behavior. Additionally, the sieve analysis of the all base course materials do not satisfy the minimum requirements of ERA specification except at station of 9+600-9+800. These results for subgrade, subbase, and base course materials that were tested with modified Proctor test and their samples compacted in 5 layers in a mold by a hammer in accordance with specified nominal compaction energy. So the dry density was determined based on the moisture content and the unit weight of compacted soil. The water content at which this dry density occurs was termed as the optimum moisture content, OMC. They also used the graph of moisture content versus dry density to determine their maximum values by graph reading. 6.4 Cbr Test with discussion. And also, the Cbr test results fail to satisfy the minimum requirements of specifications at 5 stations of 10+200-10+400, 27+900-28+100, 32+100, 32+300, 47+400-47+600 and 41+000-41+200, and at the remaining 3 stations it satisfied. This also implies the materials which are not uniformly graded. In conclusion, the base course material is not in a good performance and also it can be possible cause for distresses. The results of the Cbr tests for subgrade soils in Table 15 show that samples from all stations have Cbr value of greater than 5%. Based on the ERA specification, these samples indicate as good subgrade materials. The percent swell test results also are below 2%, which is an indication of less expansiveness of the soil, which is a good subgrade material. All values satisfied the minimum requirement, but variations of Cbr result for different conditions indicate the surface layer is affected by some other factors. For instance, for the subsection of Budge-Badatai, the Cbr value each station for very good condition is 7, for failed condition it is 10.5 and for very poor condition it is 13. Here for all surface conditions the Cbr value satisfied but the surface is distressed. Therefore, the cause for the distress is not the subgrade material but affected by other cause. In ERA standard, the minimum SOAP Cbr for sub-base material shall be 30% when determined in accordance with the requirements of OSHTO T193. Sub-base material results of stations 1 plus 600-1 plus 800, 32 plus 131 plus 300, 33 plus 633 plus 800, 41 plus 000-41 plus 200, and 47 plus 400-47 plus 600 shows the results of the Cbr value of less than the minimum requirement of ERA standard for sub-base materials, 30%, and the remaining stations satisfy the ERA requirement. But for different condition the value of Cbr vary accordingly. For example, for subsection of Bujbadatai, the sub-base Cbr value for failed condition, 24, is greater than the Cbr value, 21, of very good condition. For both conditions the sub-base material do not satisfy the requirement but the Cbr value for the failed condition is relatively good. This implies that the surface layer is failed not only by the material quality but due other cause. Base course material results of stations 10 plus 200-10 plus 400, 27 plus 900-28 plus 100, 32 plus 132 plus 300, 41 plus 000-41 plus 200 and 47 plus 400-47 plus 600 shows that the results of the Cbr value of less than the minimum requirement of ERA standard for base course materials, equals 100%. And the remaining stations satisfy the ERA requirement. However, for example, for the subsection of Alaba-Sodo, the Cbr value of the base course material satisfied the requirement at station 1 plus 600-1 plus 800 and 9 plus 600-9 plus 800 but the surface is failed. This indicates that the surface layer is getting failed due to the material by itself and the surface layer affected by other unknown cause. 6.5 Aggregate test results with discussion for base course. According to ERA FPDM, a maximum value of ACV shall be 25 as per BS 812 to 110, 1990 standard. A maximum value of aggregate flakiness index shall be 35 as per ERA specification manual. The Los Angeles abrasion value shall not exceed 45% when determined in accordance with the requirements of OSHTO T96, 99. Standard and AIV is shall not be greater than 30% as per BS 812 to 112, 1990 standard. Therefore, aggregate test values shown in above Table 16 fulfilled the requirement of the above-mentioned specification or standards and coarse aggregate particle are in a good condition based on the objectives of the above tests. 6.6 Maintenance options for pavement distresses. The pavement maintenance in general consists of all the routine repair tasks necessary to keep the pavement, under normal conditions of traffic and normal forces of nature, as nearly as possible in its as constructed condition. Department of the Army, Trademark 5-624, 1995 suggests maintenance options for different distress types with respect to their severity level. The following table shows maintenance option for cracking, surface deformation, disintegration, and surface defects with their severity level. 7. Conclusion and recommendation. 7.1 Conclusion. The pavement condition survey along the selected road sections showed that the different failure types such as alligator cracking, rutting, edge cracking, potholes, slippage cracking, block cracking, weathering and raveling, shoving, lane/shoulder drop-off, and depression were existing. The alligator cracking and rutting types of distress were dominating types of distress along the stretch. Based on the pavement condition survey, 1.41% of road section was with PCR of excellent, 5.63% of very good, 14.08% good, 23.94% of fair, 28.17% of poor, 21.13% of very poor and 5.63% failed. The average PCI values for Alaba-Sodo, shown Buj, and Bujbadatai were 36.27%, 50.32%, and 34.35% respectively. The laboratory test results show that only the subgrade material satisfied but subbase material at some stations did not fulfill the strength test, Cbr, requirement, and the base course material did not satisfy the Sieve and Cbr requirements as per ERA, OSHTO, and BS standards, and these could also be one of the causes for the distress. The road section were full of distresses, dominantly alligator cracks, surface rutting, and depressions. Therefore, these failures can be maintained by observing level of severity as per maintenance option already maintained. 7.2 Recommendation. Finally, the following points are recommended. Accordingly, existing road needs maintenances by the Ethiopian Road Authority or any concerned entity. The pavement condition ratings should be updated every year, and routine as well as periodic pavement maintenance practices should be employed to reduce premature pavement failure. The surface course, which is a mixture of aggregate and asphalt, should be considered in order to know causes of distresses in full confidence. So aggregate tests and bitumen tests for this layer should be conducted. Further study is recommended that is related with other expected causes of failures such as moisture variation within subgrade and pavement materials in order to select the most effective maintenance and/or rehabilitation techniques.